seen limits be a very important thing. We have to be able to calculate limits from left and right, and limits at 0, and limits at infinity, and all these different limits. This section is actually talking about how to evaluate limits that we otherwise could not. Now, we've seen situations where we couldn't evaluate the limits. We know that in general, we like to just be able to plug in the number, but sometimes we can't because we get 0 on the bottom. And so we had to try to simplify it first to get rid of those problems to get to the point where we could just plug in. But sometimes that isn't an option. Okay, let's say I had the function the natural log of x over x minus 1. If I tried to define the limit as x approaches 1, the natural log of 1 is 0. And on the bottom, I would get 1 minus 1, which is 0. 0 over 0, we actually don't know what that turns into, because can you have 0 on the bottom? No. So we've tried techniques like factoring and reducing, but are you going to be able to factor and cancel here? No. We've tried things like multiplying by a conjugate, but is that going to help me here? No. So nothing I have done up to this point is going to be useful in trying to calculate this limit. But this is a special case. When we have a 0 on top and bottom, this is called an indeterminate form. And this section is all about these indeterminate forms. And there are certain ones where we have a technique to be able to solve them. We've done some of these already, like I said, by multiplying by the conjugate, factoring and reducing. But when that's not an option, so if all the other stuff we haven't done, or that we've done is not an option, then we might be able to use what's called L'Hopital's rule. So L'Hopital's rule says if you have differentiable functions, so the derivative exists, then if both of them approach 0, so if it's 0 over 0 or positive or negative infinity, so infinity over infinity, negative infinity over infinity, negative infinity over negative infinity, it doesn't matter the plus or minus. But if it's 0 over 0 or infinity over infinity, then we can use L'Hopital's rule. And it tells us that our limit of this quotient is actually the same thing as the limit of their derivatives. So we will check to see, first of all, if we can evaluate our limit. Because I'm still going to throw some in that other techniques would work for. Or maybe you'll just be able to plug in and make sure you're checking things like that. If we can't evaluate it, we'll see if it's one of these special types, 0 over 0 or infinity over infinity. Then we can apply L'Hopital's rule. We're not doing the quotient rule here. We're not doing the derivative of the entire function. It's just derivative of the top over derivative of the bottom. And then that will oftentimes give us something that we could evaluate. So that example that I just gave you, that we've already said, we know the natural log of 1 is 0. I'm sure you guys remember that, right? Remember your natural log graph looked like this. Yeah, you guys didn't forget that, did you? So that's our natural log function. So currently, if I just plugged in, we get 0 over 0. That is one of the special cases, so we can do L'Hopital's rule. What I typically do is I write LH to show when I do L'Hopital's. Good idea, because algebraically these things aren't equivalent, but if we use the L'Hopital's rule, the limit is the same. So we can do the limit as x approaches 1 of each of their derivatives. We're not doing the quotient rule, just the derivative of the top and bottom separately. It's been a while. What's the derivative of the natural log of x? 1 over x. What's the derivative of x minus 1? 1. So if I simplify that, 1 over x over 1 is just 1 over x. Can I now plug in my 1? So I can plug in so the limit disappears and my answer is 1. So we wouldn't have been able to do that from the beginning, but if we first apply L'Hopital's rule, we can get to an answer. Is that one okay? Let's try the next one. Limit as x approaches infinity of e to the x over x squared. So on the top, if I plug infinity in, what is e to the infinity going to? Infinity. E to a power, the bigger the power, the bigger your answer. Okay, on the bottom, what's infinity squared? Just infinity. So can I use L'Hopital's rule? Yes, if it's 0 over 0 or infinity over infinity. So please put the LH to show me that you're doing L'Hopital's. We have limit x approaches infinity. What is the derivative of e to the x? What is the derivative of x squared? All right. So now let's evaluate. What's e to the infinity? Infinity. What's 2 times infinity? Infinity. This is still an indeterminate form. So what do you think we do? We could do L'Hopital's again, couldn't we? It still meets the requirement. In order to do it, it has to be 0 over 0 or infinity over infinity. It's still infinity over infinity, so we can do L'Hopital's again. What's the derivative of e to the x? What's the derivative of 2x? So now the top is going to infinity, but the bottom is just 2. What's infinity divided by 2? Infinity. So there's not a requirement that you can only do it one time. As long as it's still an indeterminate form, you can keep doing L'Hopital's. Questions there? Let's look at the next one. Limit as x approaches infinity of the natural log of x over the cube root of x. All right, so first we always check to see, can we just evaluate this? So if I just plugged in, what would be the natural log of infinity? Infinity. Remember I drew that natural log graph on the first example. As it goes on, it just keeps going up. So that's infinity. What's the cube root of infinity? Still infinity. So this is an indeterminate form. All right, what's the derivative of the natural log of x? 1 over x. All right, the cube root of x. Remember, that's like x to the 1/3 power. So the 1/3 comes down, x, subtract 1 from the power, -2/3. I would clean this thing up a little bit. 1 over x over 1/3 x to the -2/3. So that x to the -2/3 will go on the bottom. How do you divide fractions? So this is like 1 over x times 3x to the 2/3 over 1. If you have x's on top and bottom, what do you do with their exponents?
Or add.
If they're both on the top, you add them. If one's on top and one's on bottom, we subtract. This is next to the first, so that's bigger, so it'll end on the bottom. 1 minus 2/3 is 1/3. So this gives us 3 over x to the 1/3. All right, So the top is going to 3. What's the bottom going to? Infinity. Is that something I can do L'Hopital's with? No, it's not an indeterminate form. But we can figure this out. What happens if you take 3 and divide it by a bigger and bigger and bigger number? Yeah, anytime you have a number over infinity, it goes to 0. So I highly recommend simplifying within these as much as you can, especially if after you do L'Hopital's, if you have fractions and fractions, clean that up a little bit. Use your algebra to clean it up so that we can get to an answer. All right. Let's try a few more. Have to think back to your trig functions. What's the tangent of 0? Your handshake. Sine over cosine, so it's square root of 0, it's square root of 4 is 0. So tangent of 0 is 0, minus 0 is 0, over 0 cubed is 0. So 0 over 0 is indeterminate, so we can do L'Hopital's. What is the derivative of tangent? Minus the derivative of x is derivative of x cubed. Okay, so we need to be able to put this in. So secant is the reciprocal of cosine. What is the cosine of 0? 1. So secant of 0 is 1. So on the top I get 1 minus 1, which is 0. On the bottom, 3 times 0 is 0. What do I have to do? Do it again. All right. So, I'm going to do L'Hopital's again. Secant squared. Okay, so the exponent comes down, so that's a 2. Inside stays the same. Subtract 1 from the power, so it's just to the first, times, what is the derivative of secant?
Secant tangent or something?
Secant tangent, yeah. This is a good section to bring back all these trig functions and logs that we haven't done in a while. Minus, what's the derivative of 1? 0, so that goes away. Over, derivative of 3x squared. Okay. So, as far as cleaning this up, there's not much you can do except secant times secant. Make it a secant squared x, tangent x. All right, does this help me? If I plug in 0, secant of 0 is 1, tangent of 0 is
0.
So the top is 0, the bottom 0. It's not so great, is it? If we keep doing L'Hopital's, what's going to happen? Is it going to get prettier? No, we're going to have to do a product rule. It's going to get really ugly. So I put this one on here because I don't want you to have the idea that L'Hopital's rule is always the easiest option. Remember, we've done things like this before. And we had other options available to us. We know that if you have the limit of things being multiplied, you can split them up and do the limit of each one separately, right?
Yeah.
Okay, so let's decide how I might want to split this up. When we did secant squared, didn't we get something nice there? When we did plugged in a 0, that just turned into a 1. So 2 over 6 reduces to 1/3. So I'm going to break this up as secant squared x over 3 times limit as x approaches 0 of tangent x over x. What's this turn into?
1/3.
Mm-hmm. Now this is still 0 over 0, so what do I have to do for that part? L'Hopital's. So the derivative of tangent is secant squared over the derivative of x is 1. So we are in good shape now. So we have 1/3 times secant of 0 is 1 over 1 is 1/3. That one was definitely a couple steps harder than the ones we have been doing. But I just wanted to put it in there to illustrate that we can do things we've done before. You know, sometimes you might be able to factor and reduce things at the very beginning, and that might be a faster option than L'Hopital's. When you're using trig functions, if it starts getting nasty, see if you can break it apart. You know, this limit we could easily calculate, and that saved us from having to do a product rule, because then we were just left with tangent x over x. So clean it up whenever you can. Simplify as much as you can. One more. So the limit as x approaches pi from the left of 1 or of sine x over 1 minus cosine x. Okay. Sine of pi. If you're rusty, may be useful to go back and look at those graphs that we did at the very beginning on some of this. Remember the graph of sine? It's like this. How does the graph of cosine look? What's different? Where does the graph?
Starts
Cosine starts on this down. So if you're rusty on some of those values, this might be helpful. So sine of pi is 0. Cosine of pi is -1. So that's 1 minus -1. That's 0 over 2. Do I need to do L'Hopital's? No. 0 over 2 is just 0. So you're not going to have to do L'Hopital's on every problem. Check. Make sure it's an indeterminate form. Sometimes you might just be able to evaluate it. I want to give you guys time to do this homework, and I don't want to throw too much at you at once. So we are going to stop here for today and just have you practice this basic part or the beginning part of L'Hopital's before we move into anything else.